students, there's one topic left for Chapter 8 I must mention, and that is the t-procedure, or t-distributions. All right, so basically, this is used whenever we don't know the standard deviation for the population, and we need to construct a confidence interval. All right, so in this case, here's the problem. What happens, more realistically, when we don't know the standard deviation for the population? If the standard deviation for the population is unknown, we only have sample data to estimate the values of the sample standard deviation. And that's probably not really close to the actual standard deviation, especially if n is really small. If n is pretty large, then the sample standard deviation would be reasonably close to the population standard deviation. And the sample distribution of the mean, the sample mean, would be approximately normal. So what happens when n is small and we don't know the standard deviation? This is what we know. This is our formula for t. It's a formula to find the value of t. Basically, our sample mean, take away our population mean, divided by our sample standard deviation, divided by square root of n. And then this is the formula for z. We're looking at z. This is the value. This is the formula for it. So it's our mean, subtract our population mean, divided by the standard deviation. If you notice, in t, it's a lot more spread out. Like the range here is a lot wider than in z. And that's because we don't really know the population standard deviation. So for that reason, we got a wider range that it could possibly be. And it definitely starts to spread out more on the edges here compared to what the z value is. This procedure was created by a guy who made beer, Guinness beer in England, a guy named William Gossett. Basically, his company was having issues understanding how different the standard deviation was of the product they were making. And he came up with this way of actually getting a good idea of what that standard deviation needs to be to continue making the beer the exact same way. So just a little fun fact about where it comes from. All right, so some keywords to know about the t-distribution are degrees of freedom. Just for the record, the degree of freedom is n minus 1. And it can be kind of confusing, but just know this. The degree of freedom basically tells you how many variables are allowed to vary when we actually calculate this t-distribution. So if, let's say, n was 25, that means our degree of freedom would be 25 take away 1, or 24. That means there's 24 variables within the calculation of that data set. They're allowed to kind of be varied, kind of differ, not have to be set in stone. Anyway, I hope that makes sense. So we'll talk more about degree of freedom, and we have a table for it, just so you know. And it's this T table. It gives you the degree of freedom for 1, 2, 3, 24, the one we just looked at. And it has a confidence level, 50 all the way to 99.9. We're going to usually use 90 and 95 and 99. But we're going to talk about how to use this towards the end of the video. All right, so the T statistic here has a distribution of degree of freedom n minus 1, and the statistic will be approximately normal. N minus 1 distribution, as long as the sample distribution is approximately normal. All right, so basically all the conditions for Z still applies. Like it has to be independent. The values have to be independent from each other. The condition, that's condition level. It has to have n has to be greater than or equal to 30. So that's another condition that has to be met. Another condition is the 10%. The 10% condition has to be met. So all those conditions have to be met in order to use t-distributions. Now, if n is greater than 30, nothing to worry about. The sample will be approximately normal. We looked at that enough in chapter approximately. Anyway, that says approximately normal. We looked at enough in chapter 8 to know that we got n greater than 30 is approximately normal. Now, when n is in between 15 and 30, we actually can still use it if we graph it and we saw that the shape still looked pretty close to normal and we didn't have any outliers. We can still use it if we got no outliers. If we mentioned that no outliers, and if the problem mentioned that the shape is normal or approximately normal, and they mentioned that no skewness. And give you any of those rules, skewness, give you any of those rules, you can still use our t-distribution and all the values if all that is true. And if they say n is less than 15, the only way you can still use the t-value if, again, they say that it's approximately normal. If they say it's normal, we can still use that t-value given that information. All right, and the last thing is making confidence intervals with t-distributions. All right, so this formula still apply. Our statistic, whether it be p hat or x bar, and it's going to be our critical value. Ordinarily, it was z star, what's plus or minus. Ordinarily, it's z star. Now we're going to use t star times our standard error, and our standard error is essentially our standard deviation, whatever that standard deviation is. So it's probability. You can use probability standard deviation formula. If you know the standard deviation of the sample or the population, you can use this formula. So it's going to be still that. So this is what we're going to use to find t and z, or find the maximum number you need to have for that margin of error. Now, let's actually get practice using the table in our calculator. This says, I'm zoom in a bit. This says, determine the critical value from the table if the confidence level and the sample size are respectively, got a confidence level 95% and an n value of 21. Now, on your test, you're going to have this table, and basically you're going to go to n is 21. N is 21. Our degree of freedom should be 21 minus 1, which is 20. So what we're going to do is we'll go to our table, and we're going to go to 20. And this is the row with 20. And then we're going to go to where the confidence level is, they said 95%. So we'll go to 95%. Here's 95%. Here's the line for 20. They meet right here. So that t star value, our critical value, is 2.086. So that critical value is 2.086. So you're going to find that for each one of these on the table, you're going to use the table for it. Now let's talk about using the calculator for it too, though. So you can use the table for it, or you can use the calculator for it. You use the calculator, turn it on, of course, and you can hit second, bars, and you're going to look for inverse t. All right, so if I said 95% confidence level, think about what that 95% confidence level is. They ask for area, so here's my 95% confidence level. So the area we're looking at, in this case, is this port, which is 2.5%. 2.5%. So that decimal is 0.025. 2, yep, so 0.025 is that area there. So my area is 0.025, 0.025. My degree of freedom, we said, was 20. So plug in my degree of freedom would be 20. And it should give me, it says negative, but we can use a positive, 2.086. And that's what we said it was, 2.086. Now, of course, I rounded a bit. But yeah, that's how we're going to find our t star value using the calculator and using the table. All right, one last thing to mention. Before I go on, pause the video and find the t star value for each one of these all the way through F. And we'll talk about it in class. But right now, find the t star value for all of those in the list. When you get done, click play on the video. All right, here's the example. All right, so hopefully you answer those. Here's our example. It says Julia enjoys jogging and has been doing so for over a period of several years. During the past year, Julia has recorded her times for running 2 miles. She has a random sample of 24 of those times with a mean of 15.6 minutes and a standard deviation of 1.8 minutes. Determine a 95% confidence level for the entire distribution of Julia's 2-mile running times over the past several years. So in this case, we don't know the population. We only know what's happening in the sample, which is awesome. It's really amazing. We can make predictions or make a confidence level for the whole population, taking just this one sample of 24 different times she jogged. So basically, we're going to use this formula. So we're going to use our mean, our sample mean. So that formula has our sample mean plus our critical value, or plus or minus, our critical value, T star, and our standard deviation. So our sample standard deviation divided by square root of n. So that's all we know. That's all we have is our sample standard deviation. So we're going to use that to be good enough to go forward from there. All right, let's do this. Her mean running time in her 24 samples was 15.6 minutes. So I'm looking at 15.60 plus or minus. The T star value, our degree of freedom is, she's got 24 minus 1. So our degree of freedom is 23. And our confidence level is, we want it at 95%. This is our confidence level. So our degree of freedom is that, and our confidence level is 95%. It's going to be easier, I think, using the table, because I don't have to think about what the area is. I mess up the area. So I'm going to pull out the table instead. So going to that table, that degree of freedom was 23. So here's the degree of freedom of 23. And we want it at 95% confidence. Here's 95% confidence for that value. So there it is. 2.069 is that critical value for T star. So 2.069. We know our sample standard deviation. That number is 1.8 divided by the square root of 24. All right, and we actually found that confidence level. I would just plug this in the calculator. 15.60 plus this, and then subtract that. So let me do that now. So I'm plugging in 15.60. I don't really need the 0 plus 2.069 times 1.8 divided by the square root of 24. And on the high end, we have 16.36. And on the low end, we have, take that same equation. We'll type that same equation, use subtraction instead. So on the low end, we have 14.84. So 14.84. All right, so that would be the confidence level, confidence interval, given that T value for the population. I didn't check whether or not it's independent. It says Julian George jogging and has been doing so for over several years. So during the past, we're going to assume it's independent. She's been jogging several years. We're going to assume that she's in shape enough that jogging today and then jogging 2 days from now is not going to affect her time on the next time she jogs. So given information, just the fact that she's very experienced at doing it, we're going to assume that's independent. It did say it was random, so that's very nice to know. And because we've been doing it for several years, we can assume that 10% rule applies. So 10% rule is checked off. And it is random, so that's checked off. What we don't know is they never said that it was normal. They never said her running time was normal. They never said whether or not she had any skewed values. Like some days she might run really slow, or some days she might have the wind to her back and be running really fast. They did not give us any values, the information to say that. So technically we could have stopped and said can't be calculated with T. So we could have just stopped right there, because we don't know if that was really normal or not. We did it anyway, and we got a range there. But because that n value is less than 30, it's actually in between 15 and 30. So what was really important is that no outliers and the shape is already normal. And we don't know that. So we could have just stopped while we're ahead. Anyway, that's how you calculate it though anyway. That's how it works. I hope it helps. See you in a little bit.